Hey everyone, and welcome to your lecture on kinetics. We've wrapped up our discussion so far on kinematics, which is explaining our observation of motion, not using forces in our discussion. And a lot of you might have already struggled with this, or students typically struggle a little bit with trying to explain what they're observing, especially when we're talking about biomechanics and the application of physics to human movement. They have challenges in kinematics because intuitively a lot of us want to use force and using force to explain the motion and the movements that we're seeing humans produce. However, that was not the case. It is now, as we get into kinetics, we can use the language of force to describe how the motion that we're observing is occurring, right? Before it was just what are we seeing, and now we can say how is that motion occurring. So this is what we're diving into. One of the main ways that we're going to be able to do that is by discussing Newton's laws. And Newton, what we know as Newton's laws was the Philosophiae Naturalis Principia Mathematica. And it was these, I believe, three large dissertations covering this and Newton's three laws and a number of other ones. And it all came about because of a bet. And I kind of like this story. I think this is the fun part about history is one, kind of the stories or the tales that continue on. And I think this is a kind of an interesting one in the world of science because so much of how we understand our macroscopic or larger physics in today's world is because of this, right? So, and if you think this is interesting or are kind of curious about a lot of Western science and history, there's a really good book by Bill Bryson called A Short History of Nearly Everything. It sounds quite cumbersome to get through, but it's actually a fairly interesting read and pretty easy read. Very accessible, but it's kind of one of the places where it explains this. So anyway, so Newton, so it actually wasn't Newton at all. It was a few other academics at the time, and of course there were a bunch of wealthy individuals who could be scientists. That's kind of who did science back in the day. It was just very well off individuals who typically got into geology. The science of geology was kind of a big upper class sort of area of interest when it came to academia in the 17th century, 16th, 17th century. And anyway, so but there's other areas of interest, and one of them that came up between these three gentlemen was this idea of trying to explain the path of the planets and their orbits in space. To do so, of course, you need to prove it mathematically. So there's this kind of contention between a couple of them making this like month or 2 months worth of wager or income wager, so whatever that was at that time. And more or less what it was is the one guy was like, okay, I think it's elliptical, but I'm a terrible mathematician, but I do know someone who's really good at math. I'm going to go visit him, see if he can figure this out for me. And so he goes and finds Newton when he's working, I believe at Oxford, could be Cambridge. And was like, hey, Newton, I was really hoping to prove that the planets are elliptical. Could you help me figure out the math for this? And of course, Newton was like, oh, yes, I've already had that figured out like a couple of years ago. Let me find it. Searches his office and like the papers and stuff. Like, oh, I can't find it. Let me just redo it for you. And so he ends up doing that, describing like gravity and the path of the planets, but also writing the Principia in this kind of obsessive kind of manic kind of obsessive sort of phase that he's in to do with physics and what we now know as Newton's laws of physics. So kind of interesting. Again, like this all came about based off a bet in a coffee house at this point in time. Newton primarily at that point in time was really interested in turning simple metals into gold. So that was kind of a main obsession that occupied a lot of his time, but fortunately he spent some time down this path as well. So yeah, a little bit of a fun story about Newton. He also did weird things with optics and his eye sockets and stuff like that, but I'll leave that for you to maybe explore on your own time. So here we are. We have Newton's 3 laws, and we're going to explore that, some background on forces in general, but also diving into Newton's 3 laws. Okay, so as I already explained, kinetics is the study of forces on objects. We'll take a look at what that looks like. We're going to explore some things a little bit called free body diagrams. We're not going to get too much into that, but we're going to understand a little bit how we can draw forces. We'll figure out the types of forces, then we get into Newton's 3 laws and kind of exploring those concepts and how they apply to things that we see day to day in everyday life. So if we take a look at a force, what is it really? Well, a force is just a push or a pull on an object. It's pretty, I would say, relatively straightforward in that sense by that definition. And it is a vector. So that means it has a magnitude and directionality. So we can represent force with vector arrows, very similar to what we were doing with, say, like acceleration and velocity previously. And again, the larger the arrow, relatively speaking, the larger the force or velocity or acceleration, and the direction obviously gives it directionality. And on that note as well, when we're looking at like a system such as a person pushing or pulling a table, one thing to keep in mind, unless we're specifically like in the question or trying to finalize that, is we really need to define our system and state what aspects we're analyzing. So unless otherwise stated, typically we look at the whole person's body creating a force. So we kind of summarize or summate all the internal forces to one net external force. Whether it's a push or a pull. And then that way we can, not have to worry necessarily about the exact force going through the left or right foot or the abs and the core kind of pressing forward, the triceps, etc. We just summarize it as one. There are certain questions that we'll break down, but we'll just be looking at one limit at each time when we go to do that, okay? And of course, I think the last most important part about force before we move on is, of course, our SI units. So important. Again, make sure you're definitely including that in your answer, if not while you're doing your calculations, and that is our Newton. Okay, so we have 1 kilogram per times per meter per second squared. Okay. And that's how we can break it down. But again, typically we'll talk about Newton as newtons. Okay. All right. So I mentioned again earlier that forces can be vectors, or they are vectors. Because of that, if we have a vector force that's on an angle, very much like what we did with our velocity, typically, or acceleration, is we can look at our two component, our x and y components of our angular force. And when you get to your lab and start using a force plate, you're going to explore this idea a little bit more. But again, we can have two different directions, so an x and y kind of axis that summate to be an angular force or a resultant force, or a net force or total force. All of these terms can mean the same thing. And then we have our x and y components of that, okay? One tool that is sometimes helpful is when we take what we'd normally draw maybe on a diagram or a schematic, if you will, kind of here, is we can put a center spot, so that would be our kind of center axis of all our forces, and we can add on our forces to that center point to generate something called a free body diagram. And as you can see here, we just simply take the tail, so not the tip, but the tail of each of our forces, and put it to that center point. And then we can add them on all there. One of the useful things about that process, again with two forces involved, maybe not as helpful. But when we look at some scenarios that are maybe a bit more complicated, so let's say a weight force and a normal force, we'll talk about what those are in a bit, are opposing each other and they're on different things. To summate all the forces in that scenario, we can make a free body diagram. It becomes a little bit more apparent which direction those forces are occurring. But also if we look at something with multiple forces in one direction, we can actually summate them on our free body diagram, kind of as you see here. So each of the tires have a normal force acting against them in an upward fashion. So we put all the normal forces here. You can even add them on tip to tail as well, although this is one more common format of doing that. And then again, the idea is you can see which direction every force in a schematic or a drawing works in a diagram format. That's pretty much it for that. Okay, so we can kind of take a look at this again, much like our velocities, we can sum forces and that gives us a net force. Here we can see we have 3 newtons in a negative direction, let's say, and 3 newtons in a positive. You add them together, you have 0 net force. We'll just talk about what that looks like later as far as describing what forces look like. Here, if we were to sum our forces, we could have 3, let's say, in a negative direction and 9 newtons in a positive direction. We add them up, we have 6 in a positive direction. So this little zigzaggy sort of sign, it means sum, or this sum of forces is our net force. And what that means is it equals all the forces, however many happens to be involved. Well, there's only 2 here, but if we had 7 different forces, we could add them all and we would sum our forces, and that's what they would be. Okay, and the negatives obviously subtracting, the positives adding, and that would give us our directionality. Okay, great. So let's talk about the types of forces that we can have. Now, classically, there's 4 main categories of forces. Gravitational, electromagnetic, strong nuclear, and weak subatomic. We, for this class in biomechanics, aren't going to worry about the more atomic level ones, so the strong nuclear or the weak subatomic, but we do still need to keep in mind a little bit of things at an atomic level. And again, we'll cover the basis of what that looks like in a moment, but that helps us explain our electromagnetic forces that are involved. And even as our whole body and our physiology works, a lot of how we produce movement internally is through electromagnetic ways. Again, it's maybe not a direct kind of understanding of how forces are produced in the body, but our nerve transmissions are electronic because of the flow of ions. And then when we're actually contracting our muscles, we use a lot of chemicals. So even if we just look at ATP, that helps create energy within our muscle contractions. And then even where we're making contact, let's say with the ground, and I don't want to get too far ahead of ourselves quite yet, but when we're making contact with the ground, that is also a form of electromagnetic contact. And the forces that are occurring at that level between, say, our sneaker, our foot, and the ground are also electromagnetic. So again, all of that kind of falls under that realm. And gravity we've looked at before, but not as a force specifically. We just helped use it to describe motion that we're seeing when we're looking at kinematics. But we'll look at it more as kind of a force in this setting. Okay, and so if we look at our electromagnetic kind of forces, we can break them into a bit of a subcategory that would be contact or mechanical forces. And for that, we'll look at a normal force, friction force, tension, primarily. Those are the ones we're going to use. And even then, we primarily just use normal and some friction. And then last but not least, there are spring forces that are involved that I would put into contact mechanical. I think sometimes some people classify that outside of mechanical forces because it has its own properties, but alas. And hopefully some of you know what that movie is from and the famous line associated with that. Very topical for our discussion here. Okay, great. So let's dive into our normal force. Our normal force is essentially anytime two physical things are in contact with one another, it's the force between those two objects that stop them from going through one another. And as soon as those things are in contact, we get this creation of a normal force. And it's always perpendicular to where those things are contacting one another. Okay, so let's kind of think about that and explore that a little bit, right? So the example here is we have this bag of dog food, or bow wow chow, as it's called here. The diagram, hilarious, great. We have the force of our hand holding up the dog food here, and then the weight of the dog food is in a downward position, okay? And again, we'll explore those two, or the weight component in a moment. So we kind of have these two forces here in our free body diagram. Now, as soon as the dog food touches the table, okay, we need some sort of force that prevents it or explains why it doesn't just continue through the table and onto the floor, right? Something is holding it up in the air on the table. So what we say is the table creates a normal force on the dog food. So again, the dog food still has weight downward, but at that same amount of force that the weight is, we have a normal force upward. And that's why we have this kind of net force of zero occurring here at the table, but also why the dog food isn't continuing on to the floor. Okay, so that's a normal force. Another example of a normal force that's a little different is if I had something like on an angle. Again, we won't do tons of this, but I think it kind of helps explain things. So we have something on a ramp, let's say a box, okay? We're gonna have a box at the ramp. Looks like this. Here's our theta, or our angle there at the corner. So what ends up happening is right along this level, I wish I had different colors here, right where the box is making contact with the ramp, we have a frictional force. Again, we'll talk about that in a couple of seconds. But we also have this contact force. So the box is touching the ramp. And because of that, we have a perpendicular force. So that means a force that is essentially 90 degrees to, so or square onto the ramp. Right, so we again have the center here, so we have the same and equal force coming away from the ramp in this kind of normal fashion, perpendicular to the ramp. Now, there's a couple other things. The weight force is this direction, right, because of gravity. So we don't have a full weight of this. We actually use cosine theta to kind of help calculate what the actual force is, normal force coming off of that, because it acts in a perpendicular fashion, but it's not square on, it's at that angle. But again, it's just one more way to describe that perpendicular, even if it's not flat, if it's at an angle, it still happens at a perpendicular angle. We just have to calculate for the angle on that. Okay, we won't be, again, doing tons of that, just an example. Yeah, okay. So how does this happen? And let's get back to that point where it kind of stops things from going through each other. Well, we can look at this level, or atomic level, between the two objects here. So we have our dog food here in the pinkish color, and then we have our table down here at the brown color. And again, if we think of these as our molecules kind of going along this way, here's the nuclei, right? Kind of drawing those in. Around we have our electron bubbles. So our electrons have this negative charge on them. And so what we have is this negative to negative kind of electromagnetic repulsion from one another. And so, yeah, there's this kind of theory, like a Pauli exclusion kind of theory, where essentially it's saying, okay, we have these two negative electron clouds, and electrons can't occupy the same space around an atom, so they repel each other, right? So because of that, we have this space between the two atoms, and they don't pass through each other. That's more or less it, okay? Yeah, okay, good. So that's a normal force, deeply explained, I think. If nothing else, when you're taking away a thought here from a normal force, as soon as things touch, if there's contact, there is a normal force. So you have to label it, you have to find it, you have to identify it, and it will always be perpendicular. So again, if this is where the contact is happening, perpendicular is this way. If this is where the contact is happening, perpendicular is that way. Okay, so whichever direction it is, doesn't matter. It always happens in a perpendicular fashion. Okay, two main things to take away from normal force. All right, let's take a look at frictional force. I mentioned, again, when we had a box on a table, and the box is sliding or moving along the table, there's going to be friction. Well, how is this friction? Well, it's essentially the contact area between the box and the surface that causes this friction. Because if you get close enough, they're not perfectly smooth. And I don't think, I have to think about it, to my knowledge, there is no commonly perfectly smooth surface. Even ice, for example, has some sort of friction on it because it's not a perfectly smooth surface. It has a very low frictional coefficient. Even then, it's not that low. The cartilage in your knee joints or any of our joints, especially the synovial joints, the frictional coefficient in those joint spaces are significantly less than even ice. So it's again, there's a lot of things out there that have very low friction, but there's still some friction. And so if you're talking about something, let's say a wooden box on concrete, there's actually a fairly high frictional coefficient. And if you've ever tried to move a slide like a wooden box along concrete, you know this. It's not something that's a weird concept to you. But if we pause and think for a moment, and again, we just are kind of looking down here at the wooden box. If we're applying a force, let's say let's make this a positive direction over here. We got our negative direction over here. So again, we're trying to make a positive directional force. Our friction is going to act in a negative way. Okay, so it's a force that opposes the force that we're applying to something. And that makes sense. Again, if we pause and think about it, if we're applying a force to something moving in a direction, our frictional forces usually stop it. Okay, so it works against that motion. Okay, there's things like frictional coefficients from something at rest versus moving. Usually moving objects have a lower frictional coefficient than things at rest. Has a little bit to do with inertia, but yeah, we won't explore that too much. But yeah, and if we take a look at something, so I think the other thing to consider with friction is that it's not always a bad thing. So we think of it typically as, it's always slowing down these forces. And in biomechanics, we think about human movement. If we want something or someone to move, we're like, good, I want to make a force and I want to maximize how much of that force I generate because I have to make that. How do I maximize that? Well, usually I want to minimize friction, right? Well, this isn't always the case. There's some cases where friction is really good. If we consider, for example, our friend here, sorry, I just looked at the character's face. If we look at our friend here trying to push a table on ice, so they're trying to push the table, I guess, let's say again, just in a positive direction. But down here at the ice level, essentially they push that and try to generate that force, but they need to push off of the ice in order to actually get the table to move that way. Well, without any friction or any forces opposing this motion happening down that way, that arrow got from bad to worse. Okay, so kind of in that direction. If we don't have any opposing forces, this would happen, right? The person would just slip, they'd fall. Yeah, so we do need frictional forces to be able to move. A good example of this would be, let's say a car at a drag strip, or racing, right? At that starting point, if you floor it, what can happen if your tires actually don't grip? Well, they spin out. And if the tires are spinning out, is the vehicle moving forward? If you can picture that image in your head, no, the car usually just sits there and the wheels spin, right? That's not a good thing if you're trying to move forward quickly. Yeah, so again, friction can be good. And something that's kind of interesting about this too, as far as sport and biomechanics is, anytime that we go to change direction. So for example, if you're running some slalom drills in soccer, or I was going to say with basketball, where you need to like quickly stop, maybe to fake out an opponent or something like that. For a long time, in particular with basketball, it was thought that the more sticky your shoes are, the better they were. So the more friction that the soles of your runners had, the better you could be. So for example, you could stop a lot quicker, change directions. You could also apply a force, and if your foot doesn't slip, like in the car example, the spinning wheels, you're going to apply that force and be able to jump up, etc. So a lot of movement in basketball was thought to really be around that. So shoemakers for a long time were trying to push the boundary of how sticky and durable they could make the soles of basketball shoes. And it turns out, after about 5 years of trying this, they got to a certain point where the research started showing that they got too sticky. So there's too much friction with the soles of the shoes, and in particular, they're following professional basketball players in this, but they also looked at Div 1 and NCAA sort of basketball colleges. And the incidence of lower body injuries significantly increased as the progression of these shoes got more and more sticky on the soles. So too much friction can also be a bad thing, right? So what would happen is the person would go to stop, their shoe would stop, but their body had momentum, and it would essentially keep going, and they'd be rolling ankles typically, right? Or pulling ligaments in their knees or straining muscle, right? So there's a bit of a sweet spot with how much friction is ideal. So so friction can be good, cannot be so good. Usually opposes force when two objects are in contact with another. In particular, for this type of frictional force, we're thinking solids, okay, when two solids are in contact. So we can have another instance where we have a fluid in contact with a solid. And once we start talking about that type of frictional force, we're actually talking about something called drag. Okay, so drag force is again when the cross-sectional surface area of an object or a person starts going through a fluid. So that can be water or air or whatever else, right? Air is technically a fluid, any gas, right? And so because of that, what happens is the molecules within that fluid, and again, it might be easier to think of water to start with than swimming, kind of like up here in this example. So the more cross-sectional surface area that is hitting or colliding as it's moving into this fluid creates more and more drag. Now, drag kind of happens in a couple of ways, but one of the ways that it happens in a different way from like surface friction, like we saw in the last example, is this kind of generation of little eddies. Okay, so these little turbulent flow of water, which actually creates a bit of like a vacuum, in a sense that it sucks back or pulls back the object a bit, right? So this turbulent airflow. So the idea is by minimizing, so there's two ways we can minimize drag, right? One is getting rid of this surface area that is in contact, right? So we kind of have contact here to here, right? So that's quite a bit of, again, we're looking at this primarily, that length. So quite a bit of drag or surface area there relative to here, right? This part is relatively small. This front part that's hitting the surface area, right? So this is much less than that surface area. Okay, so when we're looking at surface area, we can notice that there's much less of this kind of potential for turbulent water flow behind the person creating drag. Okay, so very less drag there. Again, very similar idea here with the cyclist. We have the person's torso kind of here, so we have a very long, tall surface area making contact with the air. When they get into a tucked or arrow position, we kind of eliminate roughly like a third of this area that can be turbulent airflow behind them, right? It gets much more aerodynamic. The other thing that happens here is the shape. So we notice that the shape, if we get more into like a teardrop formation, which again, we can kind of see both in our swimmer, feet here. This is kind of like a teardrop-ish. And definitely with our cyclists, we can have a bit more of a teardrop in that direction. We allow for less of a pocket behind the person, so there's less turbulent air. Okay. So again, this comes up in sport, as we can see in swimming and cycling quite significantly, but a lot of other sports as well. When we're talking about projectile motion, we would say air friction is negligible. It does come into play if you're talking about something like the Magnus effect. So when you curve the ball, right, we can kind of use a similar idea of this drag to actually change the motion of the ball and have it curve in the air. But essentially we usually need a certain level of speed or a certain density of the fluid we're moving through. So water is, I'd have to double check, but at least 3 times. I'd have to check the density, but more or less it's significantly more dense than air relative to something like cycling. But cycling, you move at higher speeds, so that velocity can create more density too, and therefore more drag. Okay, so the big take home here with drag is that the shape can decrease drag, as can decreasing surface area in contact with whatever fluid is, like the leading point of contact with the fluid. Okay. Great. So those were 2 related frictional forces. Our next force that we look at is tension force. This one's pretty straightforward, I think, in the sense that a tensional force just happens in the direction to where the force is being applied along it. And usually we're talking about something being like a force being applied to a rope or a cable or string or anything of that nature, a chain, let's say. And again, it just happens in the same direction. Okay. Okay. This last part, gravitational force. So we've gotten out of the electromagnetic kind of forces and the contact and mechanical forces, and into more of what's called a field force, in the sense that, there's gravitational fields. But I don't necessarily want you to memorize this. I think it's just helpful and important to know how gravity and gravitational force occurs. Okay. So we have 2 objects, and here they're just particles, or you can think of, I generally think of this illustration as planets. Why? Because they're in the void of space, so there's no other things around that really affect how they would act with one another. And we kind of have this equation here, and again, equations are really, really helpful for helping explain how variables and what variables are involved and how they influence certain things. So if we have our gravitational force, that's just what that F is over here, we can see that it is proportionate to the mass of the objects, and those 2 masses combine to be a product, and exponentially inversely proportionate to our distance that we have between the 2 center points of these objects. Okay, so how and why does that work? What's important here? Well, the force in one direction for one object is the same, equal, and opposite to the other. So that's one thing to kind of keep in mind. So it's an attractive force between 2 objects of mass. So the more massive one of the objects is, let's say M1, so mass 1 gets significantly larger. Let's just say it's a huge planet or something like that. The force between the 2 objects are still going to be the same. Well, they'll increase if we're increasing the mass of force 1, but more or less they're the same. It's not like the larger planet has a larger gravitational pull. No, they have the same pull on the 2 objects. It's just so much more massive and contributes to the gravitational pull between them because it's larger, right? Let's say mass 2 gets really, really small. Well, that would decrease the gravitational force between the 2 objects, but again, they're still equal and opposite to one another. Okay, the easiest way to change how much gravitational pull is felt between 2 objects is this R value, or the distance between the 2. Okay, so a little change, let's say we make them a little bit farther apart. Well, exponentially, so by a factor of a squared factor, we're going to inversely affect the force. Remember, if we have our denominator get bigger, that makes our final kind of variable a lot smaller, right? Because it's a fraction, right? So the farther apart we make these things, the less gravitational force they feel exponentially. The closer they are, the smaller our R value gets, the larger this fraction becomes, the greater the force they feel. Okay, so this is a really good question. If you are still struggling with proportionate, inversely proportionate, exponentially proportionate, any of those kind of that aspect of understanding, this is a really good equation, if nothing else, to understand and practice that component, right? Plus, it'll give you a really good idea of how gravitational force works. But okay, again, we won't directly be using this, but I think it is really important to understand because we do talk about gravity. We do talk about how gravity influences things, and we have a gravitational constant there. Okay, but again, in biomechanics, we're largely going to be talking about, just as a recap, our tension forces, some drag, some surface friction, definitely normal forces in contact force. Okay. Great. There is one more to a weight force that we'll get to in a little bit as we're going through Newton's laws here. Okay. So Newton's laws, here we are. This is a good time, by the way, if you haven't taken a break already, like take a break. It's a good reset moment, can kind of refresh your brain and stuff like that. I will be pressing forward here. Okay, so with Newton's laws, Newton's first law, drum roll, is our law of inertia, is another way of saying it. What is that? Well, Newton's first law essentially says any object that is at rest will stay at rest unless acted upon by some external force. And you can say kind of the opposite too. An object that is in motion is going to stay in motion and stay in that path until acted upon by an external force, and then it'll either change a path or slow down depending on what that external force is. Okay, so again, things in motion stay in motion, things at rest stay at rest, unless we add force to the system. All right. So I think a great example of this is this classic sci-fi movie scene where we have our astronaut in space and oh no, there's an explosion or something, and their tether comes off of the space shuttle, spaceship, space station, whatever it is, and now they're adrift in space, right? And what happens? Why is that a terrible thing? Well, they just keep going, right? Why? Well, there's no air, so there's no frictional force or drag from air. There's definitely no gravity acting on them in any significant way that will pull them back towards Earth, especially if they're moving away or whatever planet they're above, right? So they just keep going, right? And you're lost to the abyss, and that's a terrible, tragic way to have things end in a sci-fi movie and or real life. But I digress. This is a really great example of inertia, okay? And that's hard to conceptualize and picture on Earth. Why? We have so many external forces acting on objects that slow them down to come to a stop, or resist their movement when they go to start, okay? We often don't think of this thing, inertia, as being like something just going on forever, right? There's just too many external forces on Earth, often. Okay, so again, if you're having troubles picturing this first law of inertia, always picture it in space. That'll definitely be helpful for you, okay? And I think another example is kind of like an air hockey puck. If you've ever played with one, you're familiar, but essentially the air helps keep the puck elevated, so there's no frictional forces. So gravity, so the upward and downward forces, the weight of the puck and the gravitational force on it essentially cancel out. What happens? You can hit the puck and it just kind of flows right on forever, unless after hitting the bounds or hitting the boards enough, it slows down due to losing energy that way. But again, just another opportunity for you to observe inertia that way. in real life. A couple of more examples just to kind of help solidify that. When you're driving in your car and you stop suddenly, the reason your body flings forward even though your car has slowed down is your torso and your body has inertia and will keep moving forward even though your car has stopped and is not going that direction anymore. And again, inertia is related, or sorry, we haven't covered this yet, but something important to remember is inertia is related to mass. So the more massive something has, the more mass something has, the more inertia it will have, which means it will be harder to get moving or harder to slow down once it is moving, right? I like this classic scene from Indiana Jones. Large boulder. Why is that worrisome for Dr. Jones? Well, it's a very hard thing to stop, and largely because of its inertia due to its mass. Okay, and this will come into particular importance when we're talking about angular inertia. All right. Well, let's have a little check-in on that concept. Just see how you're doing. Again, I'll give the answer relatively quick, but give you an opportunity to pause here on the video, read through the question, the multiple choice, and then pick the best answer is related to the scenario down here. Yeah, again, hopefully you pause. I'll give yourself at least like a minute and a half if you need to read through an answer. Good. Okay, hopefully you've had time to do that. So as you work through this question, it kind of relates down here. Okay, so we have 0 net force here and 0 velocity here on this first vehicle. Second vehicle has some speed, kilometers per hour, not meters per second. I know, not SI units, but that's okay. We will forgive this question. And what is the force net? Is there some force being applied to this scenario or not? Well, technically here, the answer is no. So it has 0 net force acting on it, okay? And why are we saying that? Well, it has a constant 50 kilometers per hour, okay? So if we had some sort of net force, we'd expect the velocity to be increasing. Why? Well, we know from Newton's first law that things in motion will stay in motion. And again, if we have no restrictive kind of air force stopping this vehicle, I mean, look how aerodynamic that is. There's like minimal air drag, so we could probably say it's relatively negligible, although the speed is going at 50k an hour, there would be some. But again, based off the information given, we can say there's no net force. It's constantly moving at that. And yeah, so we're looking at D, okay? This raises a really good question, or a good segue into our second law, is that if we don't have any force, we do still have motion, but we know this vehicle won't be speeding up. Well, why is that? How do we talk about acceleration and forces? Wow, that is such a great question to be asking yourself at home. Well, that is because of our second law of motion, and originally stated this way. Again, this is the equation derivations. I'm always happy to work through that with you folks if you ever have any questions about those. But the primary thing is we look at our acceleration and we see that it is inversely proportionate to its mass or proportionate to the net force applied. Okay, so what does that mean? Well, that means if we increase the mass of something, that's going to decrease its acceleration and vice versa. And if we have a net force that's increasing, well, we're going to see an acceleration increasing. So we can think of the car, if we press the gas or the accelerator, well, that means we're increasing the force. We haven't changed the mass of the car, that's going to stay the same. But the force that we've applied through torque, through the engine, is going to increase its acceleration. Okay. One way that you are definitely going to be more familiar with this, most likely, is force equals mass times acceleration. Again, let's just reworked this question. So how is that saying? Well, if we want to know how much force an object with acceleration has, we just need to know its mass and how much it's accelerating. And we can know how much force is being applied to accelerate that object at a certain speed. Okay, so that's Newton's second law, and we'll take a look at how that looks in a couple of ways. We already spoke about that. Here would be an example where we have an object and we are adding mass. This is about the only time that I can kind of think where we can immediately add mass to a particular object. Typically, what we'll find is the mass of something will generally stay the same, okay? In the sporting context anyways that I was thinking about, okay? So we add on the mass of two individuals into the sled. The sled is actually pretty heavy in and of itself, relatively speaking. Yeah, and so we got our bobsledders there. But let's take a look at this diagram, because this will help explain the inversely proportionate aspect of things. So here we have our individuals, a smaller and larger individual, and that represents a smaller or larger force being produced. And we have our shopping carts, which are the same mass in both instances. And what we'll come to find is that because we have a larger force applied to a smaller mass, so let's say a larger force increases in the one case, and we keep the mass the same. If force goes up, we'd expect acceleration to go up as well. I lost my pointer, sorry. So acceleration goes up, okay? So again, force goes up, acceleration increases. The direction of the arrow just means increase, not traveling upward, just to clarify. We have these two arrows here, okay? Okay, so increasing force increases acceleration. All right. Well, what happens if we increase mass? Well, we said that was inversely proportionate, right? Here's our mass. Oh, I should erase. It's getting messy. Hold on. Let's clean up a little. All right. So if we increase mass, it decreases acceleration. How does that happen? Well, again, same force, same mass as over here. We have our acceleration. But if we increase the mass of the buggy, so we can picture that, it gets heavier. Is our acceleration going to be the same for the same amount of force? No, right? It's going to slow down with our larger mass. So again, we make mass larger. And because it's a denominator, that means we inversely proportionately affect our acceleration to decrease. Okay, that's all that's saying. Again, we held force the same. Okay, great. So let's take a look at this same idea in one more way. Okay, we have our, I'll give you a minute again to pause here. You can read through, then we'll cover the question together. Okay, hopefully you did that. Right, and we can kind of look at these equations. Okay, I think mostly people choose the basketball would accelerate greater. Why? Well, the mass component is much smaller. We can even look at this equation too, right? If we have the same force being applied, and we, so the force again has to be the same when we're comparing A and B. If in the one scenario, mass is a lot smaller, so in this scenario, in our basketball scenario, our acceleration for that same amount of force has to go up. And we can inverse that when we're thinking about the vehicle. So if the mass goes way, way up, our accelerations come way, way down for the same constant force that's being applied. Okay? Okay. Good. Yeah, and again, any of these concept checks or questions or anything in the slides, you can always ask me. Yes, there we go. There's the grand reveal. Large acceleration, small acceleration. Okay, good. Okay. Yeah, so here we have some problems, some questions kind of posed to you. Again, I'll give you a moment to read through the first one. I'll kind of give you a thumbs up. You can pause, work through it, and then we'll go through the second one in brief. I won't go through it as fully as I normally do on the board, but if you're having challenge with it, I'm more than happy to spend time and go through it step by step with you. Okay, so question number 1. Go for it. All right. So for question 1, as with all problems, the first step is to find your what you know. So we know our net force and we know our weight, okay, which should probably say mass, okay? So that would be mass. is 24 kilograms. What's the acceleration? So again, we need to know all except for one. And we look at our two equations. Well, here we have our unknown already on the left-hand side of the equation by itself. So we're going to use this one, okay? We can simply plug and play from there. So we put 51 over 24, and we end up getting something like will be like meters per second squared, okay? Because it's a acceleration, right? And if we remember back to our last part of the course, that same thing. Nothing has changed when we're talking about kinematics as far as acceleration, right? Okay, I'll let you do question 2 now. Great. Okay, so we'll take a look at this. So what is our knowns? What is our unknown? How do we get there? Well, we have our mass of our sprinter, and we have our acceleration that they're accelerating at, okay? And then it's asking what the net force is. So if we look here at our equations, here's our net force all by itself. Again, on the left side of the equation, already isolated. So all we have to do is plug and play. We take 63 kilos, put it into mass, 4.2 meters per second squared into our acceleration. And once you're done calculating that out, it should be, what I have here as an answer is 265 newtons. Okay, so again, force is newtons. Okay, good. Alrighty, I did promise this, and I've played around with where I discuss this in the lecture in a few different places. I do like it here. I should probably maybe put it in both, but I digress. So how do we tie in Newton's second law and weight to something we just discussed? Well, if we look at Newton's second law, force equals mass times acceleration, if we know gravity, or a gravitational constant, is an accelerant, and we know that, we can essentially modify ma to be mg. And once we have mg, we change this force, or our force, into a weight, okay? All weight is, when you say weight, when you're weighing yourself at home or something weighs a certain amount, all you're saying is its mass, so the physical atoms that it has a certain amount of mass, in gravity, based off the gravitational constant on Earth, is a weight. That's what something weighs. So to say that in a slightly different way, if we were to take your mass, how much mass you have in your body, how many atoms composes it, and we take you and put you on the moon, or I believe even Mars, there are different gravitational constants there, right? Much less so significantly, I think it's like 1/6 or 1/5 on the moon. It's like a third or something on Mars, or 2/3. But so anyway, so with a less gravitational constant, you actually weigh less on these other planets, but your mass is the same. Okay, so differentiating those two terms in your head when you use them and speak about them, really helpful. I know I definitely still from time to time get them confused when I'm discussing the two. But yeah, so again, we have a force, subnote G, so a gravitational force is mass times gravity, and that is something's weight. And this is a really, really important one to just know and get used to doing, largely because we are going to use this quite a bit as we get into our discussion about torque and trying to solve some torque problems, because you're going to have weight given to you, weight of a limb, weight of a book or a piece of sport equipment or a ball or something, and you're going to have to just know that if you see something's mass given to you, that you can turn it into a weight force. And that's like a really common process that I'll get you doing. Okay, good. So again, that's very closely related to Newton's second, but we can think back to our different types of forces that we were talking about and include that in there. Okay, good. Great. Drum roll. On to Newton's third law of motion. Hang on. All right, folks, this is where it gets a bit weird. All right, so Newton's third law of motion is whenever something puts a force onto another object, there is an equal and opposite force pair that occurs with that initial force production, okay? Yeah, buckle up. It's going to get fun. So the magnitude of these two forces are the same. They're just happening in equal and opposite directions. And I want to be really clear here. Those forces occur on different objects, okay? They don't occur on the same object. I want to be really clear about that. So with Newton's third, the more common way of hearing this is for every action, there's an equal and opposite reaction. Yes, but also no. Because if everything that created a force onto something else had an equal and opposite reaction, they would just cancel out all the time, right? Sorry. Apologize that if you had your headphones on, it was loud. Yeah, if it's an equal and opposite reaction, it's not gonna, nothing would travel anywhere, right? Because we'd have all these forces canceling out. The net force would always be zero. We have zero force, there's zero acceleration. If there's no acceleration, things would just stay put because all these external forces would just stop everything from moving and they just stay there, right? So how does this work? Well, these equal and opposite forces are force pairs, and those pairs occur on two different objects. Okay, so yes, how do we take a look at this? Well, for example, if someone is jumping across this cliff, as we can see in the photo, right, they had to push down from their foot onto this ledge, right? So this is onto the ledge. I should have wrote it more like this, sorry. Maybe I'll just redo that. Let's do this a little more correct. So when they push down, they push onto the ledge this way. That's one part. In an equal and opposite direction, so let's try to keep even the angle right, this way, and I tried to keep the length about the same too, the cliff pushed back onto the individual to propel them into the air. Okay, so to get into the air, they had to overcome gravity forces, the weight of their body, air resistance, let's say a little bit. It's negligible in projectile motion, but let's just add it in there. So they kind of had to overcome this amount by producing this. But because they had that equal and opposite reaction that overcame all these net opposing forces, they actually got up in the air and jumped across. Okay, all right. So again, this is a bit weird, right? So what I'm trying to say is the cliff pushed the person to jump over the cliff, not the person, kind of, right? Okay, let's take a look at this. I actually like this picture. I think it helps quite a bit. So we have a swimmer, and they just did their kick turn. So they kind of swam toward the wall, flipped, inverted, and are about to push off. And we see them pushing here with their feet on the wall. Okay, so the force of the foot on the wall is pushing this way, right? Okay, so again, the feet pushed on the wall. So the wall is experiencing this force right here. Wow, that was supposed to be a star. It is not. Okay, now the equal and opposite reaction, this force pair, based off of Newton's third, is actually the wall here on the person's foot pushing the swimmer in this direction, right? So when they bend their knees and go to extend their legs, they're creating this force, which then the wall creates this force, okay? All right, and then we see the swimmer move, okay? So something else you might want to consider too is like, why is the swimmer moving and the wall not? Well, there's a couple of different reasons, couple of different ways you could look at this. One is there's more forces holding the wall in place, right? We have like stronger structure here, it's all concrete, etc. Also, it's mass. We can think back to Newton's second law. The force that's being experienced by this wall is very minuscule relative to its mass. So again, when we see that force mass trade-off, the acceleration is very low. So it does have maybe some acceleratory forces, but based off of its resistive forces plus the fact that its mass is so large, we see that we have a much, much greater acceleration experienced by the swimmer because their mass is significantly lower. We can also say that the resistive forces occurring in this direction are significantly smaller than what the wall has as far as its resistive forces to the opposing force. Okay. Wow, that got busy quick. Okay, I tried saying that a few different ways. Again, I really feel that, again, understanding that a force pair happens on different objects explains why we don't just see Newton's third canceling all motion that we observe, right? So force pair there and there. Okay. Okay, that is it for today's video lecture. Here's some learning objectives and, of course, the equations we went through. There's a concept check on the slide deck that I gave you that you can start working through to try to understand like free body diagrams and force pairs and where to find forces. We'll start most likely next class with this. And then, yeah, there's a answer key here too for you. All right. Great. Thank you for listening. And again, as always, feel free to send me an email with any questions, or even better, come catch me after class next day. All right. Take care.